The next topic, which is quite important, is the conservative force. So what are we gonna learn here? Okay, so let me just give you some idea. For example, if I have an unknown force, okay, so if we know the function of that force, so how do we know that that force is conservative or the non-conservative force? Okay, so in these topics we're gonna learn an equation that we can use to prove that that force is conservative or the non-conservative. And another idea is, if we have a function of the potential energy depending on the x, y, and the c. So now we just want to find the conservative force corresponding to that potential energy. So how should we do, right? Okay, so let's just revise about the conservative force. The work done by the conservative force, right, it doesn't depend on the path that you have known already, but it just depends only on the initials and the final positions, right? So we say that the work done by conservative force, right, by definition equal to the integral of the conservative force and then dot product with the infinitesimal displacement, right, the vector dr, which is equal to the negative of delta u here, right? Remember, the work done by conservative force equal to negative of the change in the potential energy. Okay, so now if for the complete revolution, okay, so it means that the initials and the final positions are the same. For example, if we have an object here, okay, and then if the object just move, along this path, right, and then finally it just go back to its original position. So in this case, the initials and the final positions are the same. Okay, it means that the work done by this conservative force must be equal to the 0, right? Because the initials and the final position are the same, so it means that the u must be equal to the 0. Okay, so that's why we can just write down this integration, right, to be something like this. So you may notice that, okay, let me just finish this first. So now you may notice that we have these circles at the integral side. So what does it mean? So this is the symbol of it's called the closed loop integration. Okay, the closed loop integration. So we're gonna integrate, from the initial position, right, and then to the final position where the initials and the final position are the same. So it's called the closed loop integration here. We have an equation that we can use to check whether our force here is conservative or the non-conservative forces. If the force is conservative, right, it means that the curl of this force must be equal to the 0. Okay, if you don't remember about the curl here, so you should just revise the vector chapter. Okay, the curl of the conservative force must be equal to the 0. And then if we have the non-conservative force, it means that the curl of this non-conservative force is not equal to the 0. Okay, so the question is, how are these equations derived from, right? So the idea just come from, it's called the Stokes theorem. Let me check. It just comes from the Stokes, S-T-O-K-E-S. Okay, Stokes theorem. So you're gonna learn this one in Math 3. Okay, you're gonna learn this one in Math 3. So the idea of the Stokes theorem is it just change from the word. Sorry. it just changed from the surface integral to be the line integral. Okay, just change from the surface integral to be the line integral, but whatever. Okay, let's just ignore this one first. But okay, you need to know but the thing is, you need to remember how to use these two equations, right? For the constitutive force, the curl equal to the 0, and then for the non-constitutive force, the curl is not equal to the 0 here. So now just come to the question. We want to find the relation between the constitutive force and the potential energy in the differential form. Okay, we just want to find the relation between this conservative force and the potential energy in the differential form. So how, right? How? Okay, so let me use this relationship. Okay, let me just use this relationship. Okay, so there's gonna be a little bit of math. So we say that the integral of the constitutive force dot product with the dr, right, equal to negative of the delta u. All here on the right hand side, we just write down as the minus of the integral of the du, right? So it's just gonna be the same. Okay, because the integral of the du just equal to delta u. Okay, then if we compare the integrand of this integration, okay, if we just compare here the integrand of this integration, including the negative sign as well, then we can get that the conservative force, right, and then dot product with the dr is equal to minus du. Okay, just equal to minus du. So now let's divide this equation, right, by the dt. Okay, let's just divide this equation by the dt. Okay, so now you can see that we have the dr over the dt, right, equal to what? Okay, dr over the dt here is just equal to let's just write it down. It's just equal to velocity v of the particle, right? It's just equal to the velocity of the particle. But then how about the right hand side? Okay, so how can work out the right hand side here? So one thing that you need to know is, if you remember the potential energy, right, it just depends on the x, y, and c. Okay, the potential energy depends on the positions of the object, the same as the UG equal to the mgy or the US equal to the 1/2 kx squared, right? It just depends on the position of the object. It's not the time. Then in this case, we just want to find derivative of the u respective to the t. Okay, this is the total derivative, right? Then in this case, we need to use the chain rule. Okay, we need to use the chain rule. So how? We have that, okay, du by dx, okay, and then times the dx by dt, okay, plus du by dy, and then times the dy by dt, plus du by dc, and then times the dc by dt, and that's it. Okay, so I mean, we just use the chain rule for this one. We just find the partial derivative of the u respective to the x, the u respective to the y, and u respective to the c, right? And then we need to multiply with the dx by dt here, dy by dt here, and the dc by dt here, because the x just depends on the t, right? So that's why we just write down as the total derivative here in this case. Okay, so the dx by dt, right, in this case equal to the vx. I mean, by definition, dy by dt equal to the vy, and the dc by dt equal to the vc, right, where the vx, vy, and the vc are the components of the velocity, right, along the x, y, and the c-axis respectively. Okay, so then in this case, okay, in this case, we say that the gradient of the u, right? The gradient of u is equal to the unit vector I, and the du by dx plus unit vector j du by dy, and then plus the unit vector k du by dc, right? Okay, this is by definition is the gradient of the u here. And as well, if we say that the velocity v, right, is just equal to unit vector I and then times the vx plus unit vector j times the vy, and then plus the unit vector k times the times vc. Okay, so then if we just make the dot product between the gradient of the u and the velocity v, so what's gonna happen, right? So okay, let's see the gradient of the u, right, this one, and then dot product with the velocity v equal to, so I dot I, j dot j, and k dot k, right? So we have du by dx, right, and then times the vx, so this case I dot I. The next thing is j dot j, okay, plus du by dy times the vy, and finally the k dot k, right? So plus the du by dc and the vc. Okay, so then if you compare here to this one, so it's just the same thing. Okay, it's just the same thing. Then you will get that the conservative force dot product with the velocity v, right, is equal to negative of the gradient of the u, and then dot product with the velocity v. If you compare both sides of the equation, right, so you can see that the conservative force in this case must be equal to minus of the gradient of the u, okay, because we have the dot v and dot v just the same thing. Okay, so now for the conclusion, we can get that the conservative force is going to be equal to negative of the gradient of the u, right, and that's it. Okay, but don't forget that it's going to be equal to let me use the blue one, equal to minus the I du by dx, right, and minus unit vector j du by dy, and then minus unit vector k du by dc. Okay. So then what is the physical meaning of this equation? Okay, what is the physical meaning of this equation? One thing that you can see is, if we know the u, okay, if we know the function of the potential energy, right, then we can find the gradient of the u, okay, is going to be equal to this conservative force, that thing that we can get. But if we just want to get the insight of this equation, so how it's going to be, okay, so let's consider this this example. Find a conservative force due to the one-dimensional potential energy, the ux equal to the 1/2 kx squared. Actually, you have seen this question already. It's me the potential energy, right, of the spring. Okay, remember, it's just the potential energy of the spring. So okay, let's use this equation, the F equal to minus the gradient of the u. In this case, the u just depends on the x, right? So it's equal to minus unit vector I and the du by dx, okay, because the u just depends on the x, so it means that this term just go to the 0, okay, and then we just change the partial derivative to be the direct derivative here, so let's just use the d here. Okay, so it's equal to what? Okay, so we have the minus I here, and the d by dx of the u, right? Just the 1/2 k and the x squared. Okay, so 1/2 k is constant. We can just bring it out here, right? And you need to find the derivative of the x squared. Okay, so it's going to be equal to what? It's going to be equal to the 2x, right? And then finally we can get the answer to be minus I and then k times the x. Okay, so that's going to be the answer. So now you can see that the answer is just the same as, the reasoning force of the spring, right? Okay. Now, so let's consider this picture. Okay. I just make the plot of the u, the elastic potential energy, as a function of the x here, right? So let's say that if we consider the extension of the spring, let's say that at this position, okay, if we consider it at this position, at this point, okay, so now you can see that the resounding force of the spring, right, it just tends to go to the negative I kx. Okay, it just tends to go to the negative I kx here. So this gonna be direction of the force. Okay, so we have the Fs equal to the negative I kx, right? So it's just equal to the negative kx here. Let's just ignore the unit vector. Okay, the same thing if the spring is compressed to this position. Okay, if the spring is compressed to this position, then again, right, the F, right, equal to the minus kx, it must point to the right hand side. Okay, because here the x is negative, so that's why the F must be positive, so it just point to the right hand side here. So then this is the Fs equal to the kx. Okay, so then what can we conclude from this picture? Okay, what can we conclude from this picture? We can say that a conservative force, right, is always in direction to minimize the potential energy function. So at this point, okay, at this point, the potential energy is minimum. Okay, so let me just make it clear. At this point, okay, so we have the minimum potential energy. Okay, so if we have the particle or the spring, right, at this position here, you can see that it tries to go to this line, to this position. Okay, so this position we have the minimum potential energy. Then it has the name. This position is called the stable equilibrium. Okay, it means that this position we have the minimum potential energy, and then if we have the particle at this position, right, it's going to be the most stable state that the particle can have. So that's why I just call the stable equilibrium here. Okay, so let me just move this sentence to here. Okay, so this will be the physical meaning of this relationship. Okay, because the work done by the conservative force, right, always in direction to minimize the potential energy. Actually, okay, if we consider the gravity, let's try to do another things. If we consider the gravity, we know that the gravity, right, just point to this direction, the gravity. Okay, and we said that if we have this reference level, right, if we have the reference level here, and then we have a object, so let's say the point mass with the mass equal to the m, right, and then it's just making the displacement, okay, equal to y from the reference level here. So we said that the potential energy, right, of the mass here equal to the m, g, and y. This is the potential energy due to the gravity, or we just call it as the gravitational potential energy. Then if we just want to find the force, okay, if we just want to find the force, we can use this relationship, right? The force equal to the negative of the gradient of the u, okay? But for this case, the u just depends on the y. So it means that this and this just equal to the 0, and we have only this one, right? Then we can get that the force here equal to minus j, and the du by dy. So don't forget that, because the u just depends only on the y, right? So that's why we just use the total derivative, not the partial derivative here. And then, okay, derivative of this one equal to what? Equal to minus j, and then m times the g, right? So it means that the force just point into the downward direction here. Okay, it just corresponds to what we have said, right? Because the conservative force is always in direction to minimize the potential energy function. So at this position, the potential energy is minimum. So that's why the force try to go to the minimum potential energy. Okay, now let's look at examples. Okay, so let's consider this example. Okay, for the part A, show that the fxy, right, equal to blah 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 here is a conservative force. So how should we do? Okay, how can we show that this one is the conservative force? Okay, then we need to show that. Okay, we need to show that, as I mentioned before, if the force is conservative, right, it means that the curl of this force must be equal to the 0. Okay, but if the force is the non-conservative force, then the curl of this force is not equal to the 0. So we need to derive this one. We need to show that the curl of the F equal to the 0. Okay, so we need to set up a metric, right? Then, okay, let's write just down the curl of the F equal to what? Okay, the determinant of the, okay, here we have the I, J, and K. Okay, and now for the curl, right, we have the d by dx, d by dy, and the d by dc, right? So now for the f, okay, this is the fx. We have the 3x squared minus the 3y squared. Now for the fy, right, the fy equal to the negative 6xy, and here 0. Okay, so then let's try to find the determinant of this metric. Okay, so how, right? The idea is we just copy this one more time, but let me just use the gray colors here. Okay, so it means that I don't need to emphasize this one. Okay, so now for the I component, we should look at what? We should look at this one, right? For the I component, this one must be positive, and then this one must be negative. Okay, so we have unit vector I. Let's just start from this, and then this is red, right? We have the d of the 0 by dy for this one, right? The derivative of the 0 by dy, and then minus, so it's going to be this one. It's going to be the d by dc of what? Of the minus 6 xy. Okay, this is with the I components of the function. Now for the j components, okay, for the j components here, so it's gonna be this components, okay, and this one. Let me use, can you see it? Let me use this color. Yeah, this should be better. Okay, now for the j component, right? So let's consider this this one first. So we have the d by dc, right, of the 3x squared minus the 3y squared, and then minus, okay, this one, right? It's just the d0 by dx, right? It's just the d0 by dx. Okay, so finally for the k component, now let's use how about this one? Nope. Yeah, here. Okay, so this can go for the k components. Oops. Okay, so let's just start from this one, right? From this one. So we have the positive of the d by dx of the negative 6 xy, and then minus this one. Okay, so we have the d by dy of the 3x squared minus the 3y squared, and then close parenthesis here. Okay, so now let's compute, I mean, for each term, right? Okay, so this sure equal to 0, and this one equal to 0 as well, right? Because we don't have this is the partial derivative of the c, and we don't have the c in this function. Okay, so it means that the first term for the I equal to 0. So now for the j, right, again, so we have only the x and the y, but we just want to find the partial derivative of the c, right? So it's just equal to 0, and this 0 as well. Okay, so now for the k. Okay, so now for the unit vector k, right? The first term is, okay, the partial derivative of the x, right, of this function is just equal to negative 6 times the y. And then for this function, right, we just want to find the partial derivative relative to the y here. So this term just go to the 0, and we have this one. Okay, so minus and minus here is going to be the positive. Okay, positive. And we have, okay, the 2 just go down, right? It's with the 6, and then plus the 6y here. Okay, so then finally equal to the 0. Okay, so now you can see that the curl of the f equal to the 0. So it means that this force is conservative. Okay, so this force is conservative. Okay. Is a conservative force. So now for the part B. We need to find an expression of the potential energy uxy. Okay, we need to find an expression of the potential energy uxy. We can do the two things. You can use this equation, okay? You can just do the integration of the f, okay, respective to the infinitesimal displacement dr, right? Or you can just use this equation as well, okay? So here I'm gonna show you how to use this relationship to solve for the potential energy here, okay? Then let's use the f equal to negative of the gradient of the u, right? What is the f? The f is equal to this term, okay? So let me just make the copy and plug it here. This is the f equal to negative of the gradient of the u, okay? But now here we said that the u just depends on the x and the y, right? So we have only unit vector I and the du by dx minus unit vector j and the du by dy, okay? So don't forget that this is just the partial derivative, okay? And we doesn't have the c dependence here. Now let's compare the term by term, okay? So let's compare the components of the vector on the left and then on the right hand side of this equation. Okay, so let's consider the unit vector I first, right? We have here 3x squared minus 2y squared on the left hand side, and then here we have negative of the du by dx, right, on the right hand side. So then in this case you can see that, okay? So let's consider the x components. You can see that the du by dx, right, du by dx, it must be equal to, okay, just move this negative side to another side, right? It's gonna be equal to the negative side of the 3x squared minus the 3y squared, okay? This is for the y component. Okay, can we do the integration here? Yes, we can do the integration, right? So let's try to do the integration. If we move the dx to the right hand side, okay, and when we just do the integration, we can get that the u, okay, which is depends on the x and the y, right? It must be equal to, okay, so let's do integration of the 3x squared is equal to what? It's just equal to the x cube, right? Just equal to the x cube, and then minus the 3y squared. So this term doesn't have the x, okay? So the y here seems to be the constant for the x because this one is the partial derivative, right? Then it's going to be equal to negative of the 3x and the y squared, okay? And then again we need to add the constant, right? Because after the integration without the lower and the upper bound, right, we just add the constant as well. But now this is the constant for the x, but it can depend on the y as well, right? Because in the terms of the x, the y seems to be constant for the x, so that's why we just add the function c, okay, which is depends on the y. Okay, so this is what we get from the x component, right? So now we just want to find this one. We can find this one from the y component of this equation. Okay, so let's use here. So now for the y component of the function, right? Okay, so let's compare this to this. Okay, so we have that du by dy, right? Du by dy must be equal to, okay, we have the negative sign and negative sign just cancel out, right? It must be equal to the 6 times the x and y. So now let's try to plug in this u into this equation. Okay, so try to plug in this u into this equation, and let's see what we're gonna get. Okay, so derivative of the u, right? Okay, for the first term here is equal to the 0. Okay, it's just equal to 0. And now for the second term, right? Okay, we have minus with minus is going to be the positive, right? And the 3xy squared. Then derivative of this one relative to the y is going to be equal to 6xy, right? It's just equal to the 6xy. And then plus, okay, so now for this term, right? We have the function c, which is depends only on the y. Then there's going to be the cy, right? And then by the dy. So you see, right now we just use the derivative because this function, it just depends on the y. Okay, and then equal to the right hand side is the 6xy. Okay, this is on the right hand side. So now you can see that if we compare, right, between the left and the right hand side, the 6xy is gonna cancel out. Okay, so the 6xy here just cancel out, and then finally we can see that the derivative of the cy by the dy equal to the 0, right? It's just equal to the 0. So it means that this function c, it doesn't depend on the y. Okay, or we can say that the c, right, is a numeric constant. Okay, it is the constant in the number, not in the variables here. So then for the conclusion, you can see that the u, right, depending on the x and the y, equal to, okay, it's going to be equal to this function. So we have the negative of the x cubed and minus the 3xy squared, and then plus the cy here, which is equal to this c, right, and then plus the constant c.